For Lab 3, titled Black Hole Orbit, I was tasked with extrapolating the unknown mass of a black hole from the given motion data of a star orbiting it. This was achieved by analyzing the star's motion in VPython to find the net force in the star for all points in the dataset, and then applying Newton's law of gravitational force and the momentum principle to solve for the unknown mass of the black hole. The components of the net force and the change in momentum were related in the code, yielding the mass of the black hole, which was determined to be 3.5662 times 10 to the 31st kilograms. The primary principle involved in the extrapolation of the black hole's mass are the momentum principle, Newton's second law, and Newton's law of gravitational force. By the momentum principle, an object's change in momentum is proportional to the net force acting on the object over a time period. Thus, by extension, the perpendicular and parallel components of the net force are equal to these respective components of the change in momentum. Now, Newton's law of gravitational force universally describes the attractive force between any two objects. From Newton's law of gravitational force, the gravitational force on the star by the black hole is proportional to the mass of both interacting objects, the black hole and the star, but inversely proportional to the square of the magnitude of the relative position vector pointing from the star to the black hole. The given motion data provides x and y components of a star's motion around a black hole of unknown mass. By inputting parameters associated with Newton's second law and the law of gravitational force, a visual of the star's orbit around the black hole can be obtained. As mentioned before, Newton's second law can also be used to relate the change in momentum of a system to the net force that acts on it. This is easiest relayed through the derivative form of the momentum principle, in which the ratio of the infinitesimal momentum change to the infinitesimal time interval is the instantaneous rate of change in momentum. Presumably, the large set of motion data for the star indicates very small intervals of time to allow for an approximation of the change in momentum at a point along the star's trajectory. Furthermore, we know from the momentum principle that dp dt is equal to the net force acting on the system. These principles will be represented in the code later in the video. Before applying these principles into the computational model, a few initial conditions and values had to be updated. The mass of the star, the universal gravitational constant, the time step, the location of the black hole, which was given, is set as the origin here. Next, the assignment statement to attract given star motion data, which is downloaded to my computer, will be read here. The velocity of the star during its motion around the black hole is calculated from these assignment statements. And the second while loop is where the two fundamental principles of this lab are present. First, the initial and final velocity assignment statements are listed here as a vector quantity, which are then used in the computation of the initial and final momentum vectors by the definition of momentum. Next, the change of velocity and momentum are specified here. As explained before, the derivative form of the momentum principle states that dp dt is equal to the net force. To define the relative position vector pointing from the star to the planet at each location along the star's motion, I assigned r to equal to magnitude of the difference between the star's position and the given position of the black hole. Finally, you can see Newton's second law of gravitation here, where the force of gravity equation can be manipulated to solve for the mass of the black hole, which is here, as the product of the magnitude of the net force and the square of the relative position vector divided by the product of the universal gravitational constant and the mass of the star. Lastly, I wrote a statement to print the mass of the black hole after running the module. From running the module, an animation of the star's orbit is output in an external window along with the calculated mass of the black hole. The visual also displays the components of forces acting upon the star along its trajectory. The blue arrow represents the perpendicular component of the net force on the star, the black arrows the parallel component, and the yellow arrows represent the total net force on the star. Physically, this makes sense because the total net force in this case is solely due to the gravitational force on the star due to the black hole. Although throughout this lab we equated the parallel and perpendicular components of both the net force and dp dt, these quantities have distinctions. It is necessary to distinguish cause and effects in the system. Changes in motion observed are caused by non-zero net force. Furthermore, changes in the parallel component of dp dt are caused by the net force, and perpendicular net force causes changes in the perpendicular component of the dp dt, which accounts for the curving in the trajectory. Furthermore, the net force and dp dt also differ in the manner in which each are calculated. In the case of this system, the net force is just equal to the gravitational force on the star, so the equation from Newton's law of gravitation is used to compute this quantity. However, dp dt must be determined through a computation of change in velocity as iterated by the momentum principle. Also, net forces can be calculated from the sum of all forces acting on a system. However, dp dt must be determined from observing the motion of an object. For the second follow-up question, if a different black hole replaced the one in this problem, but the motion of the star remained the same, there would be no way to find an alternative value for the mass of the new black hole, because the motion of the star remains unchanged, thus there would be no different gravitational force to yield a different mass of the black hole. Thank you for watching.